Okay, so we're going to run through the first couple of examples for 3.2 today. So first things first, we're going to be talking about linear equations and nonlinear. Now, I touched a bit on this yesterday, but let's just go over as a refresher. So for it to be a linear equation, we're looking for the power above it to be 1. So here, x has a power of 1, y has a power of 1, same for here, same for here, same for here, and down here, here, and here. So linear equations, the power above the variable is always 1. The other thing that we're looking for is that the terms are separate. So each variable is in a separate term, which is a fancy way of saying that each part of this expression has got one letter only. So here you can see that this term has got y times z, so that is not a linear equation. And over here you can see that that one's squared, so also not a linear. Here we've got cos terms, we've got ln terms, so they are also not part of this. We want them to be single ones on their own. We don't care about the coefficient in front of it. This could be 7 squared, that's fine, as long as the x has a power of 1 above it. Okay, so looking over here at identifying which of the following are non-linear, I'm going to highlight the ones that are linear. So you're all separate terms, you've all got a power of 1, so you are a linear equation, congratulations. This one here is not because we've got y times x. This one here, they're all separate, all have a power of 1. You're a linear equation. This one's squared, so he's not. Okay, so going down here, we are now told that they are all linear equations, and we want to state the number of equations, and we'll call that m, and we're going to state the number of variables in each of the systems. So for this first one, for A, we have 2 equations, and each equation has 3 variables. For B, we have 3 equations, and each equation has 3 variables. Now, if I only had 2 here, let's say I just had no term of y there, it would still be 3. It just means that the coefficient in front of the y term is just 0. So you're looking for how many variables are in the system. Okay, determine whether or not the system is square. This one is not square because these 2 numbers are different. So not square. This one here, they are the same. So yes, square. So now we're going to determine if x is equal to 1, y is equal to -2, and z is equal to 4 is a valid solution for all equations in the system. Now, this is just a fancy way of saying that we're going to be substituting in these numbers up here into this equation and seeing whether or not it creates a true statement. So let's test the ones in A first. So -4, bracket, we're going to let x equal 1, plus -2, minus 6 of 4. So that's equal to -4 minus 2 makes -6. So -6 minus 24 is going to be equal to -30. So that one, left-hand side is not equal to right-hand side. So it's not a valid solution. Now, I can prove it in 1, and that's enough for me to say that this is not true. It just has to be false in one statement. If it's true, then you need to keep testing because it's possible for it to be true in one case and not true in another. Okay, so next one is going to be 1 plus 5 times -2 minus 8. Z is 4, so we'll put 4 there. Okay, so that's 1 minus 10 will make that minus 9. Minus 32. So that will make it -41. Also, left-hand side is not equal to right-hand side, so it's not true. Okay, and obviously for B, I would just do the same again. Just for time, I'm going to move on. But you will notice that some of them are the same, in which case you just make your statement left-hand side is equal to right-hand side. Worked example 3. Solve the following system of equations by using an inverse matrix. So here we've got a system of equations, and I'm just going to convert that into what we're used to seeing. So my coefficient matrix will become this. and it will be equal to this value matrix. Okay, another way of expressing this is I could say I have AX is equal to B. Now, using what I know about my matrix algebra, I know that in this case here, I would have to multiply this front one by the inverse of A in order to create an identity matrix. Now, the point of creating the identity matrix is if I multiply something by the identity matrix, I get that matrix again. So if I do this, then I'll have this, which is the same as this. Now, because I multiplied this side by the identity matrix first, I have to do the same to this side over here. So in order to get our values of X here, I need to do the inverse of our coefficient matrix multiplied by our value matrix. So let's work out our coefficient matrix first. Okay, now I need to do 1 over the determinant, which will be 4 times 2 minus 1 times 3. And in my coefficient matrix, now these two will switch places, so it'll be 2, 4, -1, -3. Okay, so 1 over 8 minus 3 will give me 1 over 5, bracket 2 minus 1 minus 3, and 4. So now I can pop this in over here. I'm going to leave that number at the front there, the 1 over 5. Obviously, in your book, set this out nicer. This is a little bit of a skew-iffy way to do this. Okay, but I'm running out of space. Minus 3, 4, bracket, multiplied by 12 over, 12, 14. We don't need that line in between. Now, the way I like to think about it is this number here will multiply down this row there, and this number here will multiply down that row there. So once you chuck this into your calculator, or you can go through and do all the algebra yourself if you like, just for time, I'm going to just chuck the answer in. It's going to turn out to be, this is my values that I'm solving for. It's going to turn out to be 2 and 4. Now, a good way of checking that that's the correct answer is to substitute them back in here. So 4 times 2 is 8, plus 4 makes 12, that's correct. 3 times 2 is 6, plus 2 times 4 is 8, which makes 14, so that's correct as well. So I can prove that this is true. Okay, the next question is worked example 4. Now, we're solving the system of linear equations using technology. So I'm going to go to my graphics calculator. When it decides to load. Okay, and I'm going to go into my run matrix. Now, there's a couple of different ways that you can use the calculator. Up to you kind of what you choose to do. You can input them. It just depends how many times you want to actually interact with that matrix. Because I'm only going to be using this the one time, I'm going to input it by doing math, matrix. Now, I want to have a 3 by 3 matrix. So that's this one. So all I'm going to be doing is inputting, well, I'm using the same algebra as above. I'm going to put my matrix A in, and then I'm going to put to the power of -1 to achieve the inverse matrix. And then I'm going to multiply it by my value matrix over here, which would be B. So 3, -5, 1, -2, -7, -10, go across. Okay, -6, 2, and -9. Okay, so that first matrix, matrix A, is going to be to the power of -1. And then it's going to multiply by a 3 by 1 matrix of 25, -23, and -54. Okay, and that will give me the answer of 2, -3, and 4. So in this system of equations, x is equal to 2, y is equal to -3, and z is equal to 4. Okay, moving along. So next one we're going to do, we're looking at applying a summary of our matrix algebra rules. So these are all the different laws that we can use to matrices. They're slightly different to your standard algebra rules just because of the way that matrices interact. Remember, A times B is not the same as B times A. So when we're determining a general solution for these, okay, let's do A. So if I have XA minus B is equal to C. If this was a regular equation, if I had 2x minus 1, I'd take the minus 1 across first by doing the opposite. Now, it's going to be the same here because we're going to be adding B to get it to the other side. That's going to give me, this is what I'm left with. Now, you can see that x is in the front and A is beside it, meaning that when I take this to the other side, normally I would just divide this by A, which means I'll be dividing that by A. Dividing something by A is really the same as saying A to the power of -1, which is how I'm getting the inverse. Now, just like if I had A plus B and I divide that all by C, this is like saying that. Those two statements are the same, which is why when I move this A across, it's going to multiply or divide, depending on how you look at it, all of the things in the bracket. So this is how I would input my equations in my calculator to get it to give me an answer for x. B. Now, B is a similar one as well, except we're going to be looking at what we can factorize out. Now, you can see that x is on the end of both of these expressions, which means that when I factorize x out, instead of saying x bracket A plus B, I'm going to have A plus B timesing the x. So AX plus BX equals C. Factorize the A and the B away from the X. And now that I've got it like that, I can take this matrix across by inversing its answer. Now, it's at the front, which means it should stay at the front. When it swaps sides, because it's multiplying here, it will become to the power of -1. Which is how I get this as my answer for what would need to be put in the calculator. Okay, so I'm not going to go through with the answers for these. I'm only going to show you the algebra of how you can separate x on its own. Now, it is a lot easier to do this like in one step. So instead of, putting all of these matrices in and then moving them across and then doing all of that matrix calculations each time, I'm going to move everything away from x and then I'll be left with what I need to do, what the calculation is in one go instead of multiple. Okay, so A, B plus XA equals C. Now, when I take this B to the other side, it will become a minus B. The order for this doesn't matter at the moment because when I'm adding and subtracting matrices, order doesn't matter. When I'm multiplying or using inverses, though, it does matter. So that's what I'm left with at the moment. You'll notice A is on the end here, which means that this thing, when I take this guy across, is going to become inverse A, and he's going to go to the end as well. So I'll be left with x is equal to C minus B, A to the power of -1. Okay, B. Similar to what we did above, except now instead of having a plus, I've got a minus. So it's going to become A minus B, factorize the x out is equal to C, and then when I take this to the other side, he's in the front, so he's going to go to the front spot, bracket A minus B. He was multiplying, which means now he's going to be inverse, and C like that. Okay, up here, B got to go on the end because whether I do C minus B or minus B plus C, they are the same for matrices. It's down here when they're multiplying and dividing that you'll have problems.